Welcome to the 82nd Theoretical Physics Colloquium by Professor Alexander Rothkopf from the University of Stavanger in Norway. He got his doctoral degree from the University of Tokyo in 2011. He had several postdoctoral positions at the University of Bielefeld, University of Bern, and Heidelberg University. During 2016 and 2018, he was still in Heidelberg as a principal investigator and scientific manager of Collaborative Research Center, ISO-Quant. Since 2018, he was an associate professor at the University of Stavanger, and I'm glad to tell that recently he was promoted to full professor. In 2019, he received LICE Research Award, which is the annual award for outstanding research at the University of Stavanger. Over the years, he was involved very deeply in professional service outreach activities. Between 2010 and 17, he was on the editorial board of European Journal of Physics A. Since 2019, he is a social media outreach coordinator at his department at the University of Stavanger. And in 2021, he became city coordinator and organizer of inaugural Pint of Science Stavanger Outreach Festival. His research interests include nuclear physics, real-time dynamics from lattice QCD, relativistic heavy ion collisions, open quantum systems, bound states of heavy quarks, and many other things. And today he will be talking about open quantum systems, thermometry at the extremes. And with that, I'll give the microphone to Alexander.
Thank you very much. I will share my slides. Can everybody see the slides? Very good.
Yes.
Then it is on me to thank you, Igor, for the kind invitation. It is a pleasure to be virtually attending this colloquium. It's what we do these days, and it's great to have the opportunity to talk to all of you about a topic that has been quite dear to my heart over the past years, and which I believe holds a rich opportunities for collaboration between different subfields of physics, which is open quantum systems, and here in the context of precision thermometry at the extremes. So when I say extreme temperatures, well, we could at first think about where in nature do we find extremes of temperature. And well, on the cold side, outer space might be the good place to start, where the cosmic microwave background gives us a fresh, crispy 2.7 Kelvin, so on the rather cool side. And then on the other hand, if you think about a place out there that is rather hot, the sun's corona might be where to look, where we have several millions degrees of Kelvin that we find. But both of these numbers really pale in comparison to what it is possible to achieve now regularly in the laboratory, where nowadays it is common to reach nanokelvin or lower temperatures in the study of ultra-cold quantum gases as they form, for example, Bose-Einstein condensates. And on the other hand, through particle accelerator facilities such as the LHC at CERN, formerly RIC at LHC, and upcoming facilities such as NICA and FAIR, we are able to generate for a fraction of a second, but we are able to create temperatures in the lab of around 10 to the 12 Kelvin when studying phenomena such as the creation of a Quark-Gluon plasma in such kind of heavy ion collisions. So this gives us somehow the breadth of numbers we are dealing with here in extremes of temperature. But what is temperature? And as a theorist, for me, this expression here tells it all. If I have a system with a large enough number of interacting degrees of freedom, then the density matrix of that system tells me what I need to know. It tells me the probabilistic distribution of energy by which, and it has essentially two terms. The first one is really the probability for a state with energy Ek to be realized in your systems times this representation of that state with energy Ek. And when we look, where does temperature show up here? It shows up as a parameter governing the statistical distribution of energy in our system. And so when we are talking about measuring temperature, in the end, it becomes measuring the statistical distribution of energy. And this is what thermometry is all about, just the fancy term for getting our hands on the temperature of a system. And I would like to distinguish between two different kinds of temperature measurements, starting here with what I would call the probeless measurement, where we try to measure somehow, again, the statistics of energy or any other temperature-dependent observable. And the most well-known and oldest form of this is passive imaging, the observation of electromagnetic radiation emanating from your system. If you are a blacksmith in ancient Rome and you're forging the swords for the legions, you put your iron into a furnace, and by the color of the metal as it shines, you know what is the temperature that you have reached when you have to start forging your sword. And the more modern version of this is then what I would call active imaging, where you use some sort of often coherent light source like a laser to shine light through your system and read off from its interaction with the system the temperature that the system under observation has. That is the one. That's the probeless one. Then there is the probe-based way of determining temperature, and this is how we usually associate measuring temperature in everyday life. There's the static way of doing this. So this is our good old thermometer. You have a small probe system that you bring into contact. You wait essentially an infinite amount of time until this system has become completely thermalized, equilibrated with its surroundings. You remove it and you interrogate the internal structure of your small probe. And by that, you read off the temperature of the surrounding medium. On the other hand, there's a dynamic fashion, and I would call it the Earl Grey fashion. Let's think about a sugar cube in your cup of Earl Grey. It is a small probe that you insert into your system, and that now over time becomes closer and closer to equilibrium with its surroundings. And the speed of how this progresses tells you about the temperature of the environment. And the important difference between the two is that in the latter, in the dynamic case, your probe never has to actually be in thermal equilibrium with the surroundings. And that allows you to measure temperature often on shorter time scales than with the static method. What it comes down to is really to measure then the non-equilibrium or the equilibrium properties of this small probe system that you need to understand to read off what was the temperature of the environment that you brought it into contact with. And so what we need is, eventually, we need an efficient formalism to really describe now this interaction between a small probe and our environment in the context of a quantum system that we'll be interested in. And this is where these open quantum systems really come in and shine. And what is this open quantum systems framework? Well, thanks to our colleagues in condensed matter theory who have developed this over the past decades, it is really a very general approach to describe a small probe coupled to a thermal medium. The total system consisting of the medium and the probe, it's a closed system. It has a Hermitian Hamiltonian with a probe part, a medium part, and an interaction part. And the overall density matrix of this closed system is as we would have written it in the beginning. Now, the evolution of this closed system, as is well known, proceeds according to the von Neumann equation with the commutator with the Hamiltonian, and this corresponds to unitary time evolution propagating our closed system in time. Now, because either of technical limitations or the complexity of the system at hand, we might not be interested in describing explicitly both the medium and the probe, but we would just like to know about the probe itself, because that is the object that we will interrogate in the end. And so if we want to focus on the probe, we can formally at least trace out the medium degrees of freedom to end up with what is then called the reduced density matrix or the probe density matrix. And it is then the question of how does this density matrix of the probe evolve in time? And the first take-home message here is that generically, because this probe is in contact with the surrounding systems, we are now dealing with dissipative dynamics, which requires an equation of motion that we call in this context a master equation for the density of the density matrix that goes beyond the standard von Neumann or Schrödinger equation that you have for a closed system. And of course, everything should be consistent, that if you evolve the full system and then trace out the medium, or you first trace out the medium and then evolve the probe, in the end you should get the same thing, and that should be our goal. Then the specific form of these master equations depend on the inherent separation of scales between your probe system and the medium, and there are three scales that are relevant in this context. The first one is the medium relaxation scale, which is essentially, if you perturb your medium degrees of freedom, how quickly do those perturbations die down? So this is a purely medium property. Then you have the intrinsic probe scale, which is often related to essentially the energy spacing between the internal states of your probe. So this is the inverse of the level spacing. So this is a purely probe related quantity. And then you have the probe relaxation scale, which you can think of as the scale and the time it takes if you throw in this small probe with a directed momentum into your bath, and how long does it take to randomize the momentum of that probe. And that now clearly has to do with the interaction between the probe and your medium. And so these three scales then determine the explicit form of your evolution equation.
Alexander?
Yes.
Quick clarifying question.
Yes, please.
Why don't you have an intrinsic medium scale, which might be relevant somehow as well?
Well, this would be this tau m, the medium relaxation scale, would characterize how information is updated, how quickly the states in your medium are updated as you perturb them. And this is compared usually, or the relevant comparison is then how quickly is the information updated within the states of your probe system. And these are the two timescales that you juxtapose. Did this answer the question?
I'm not quite sure, but maybe later we will discuss this in more detail.
The temperature is the scale which you ask for.
Yes. So the tau m would depend surely on the temperature of the medium, as would the relaxation scale. The intrinsic probe scale does not necessarily, that depends whether that has a direct dependence on the temperature.
Okay, thanks.
Okay, very good. And now that we've seen a very rough sketch of the ingredients and the vocabulary that goes into the Open Quantum Systems framework, let's see where it shows up in, and we do so by going to the coldest matter in the universe, where I show you here this classic plot of Bose-Einstein condensates. And this story begins in 1924 when Einstein and Bose investigate the statistical properties of bosons, and they conclude that there should exist a new phase of bosonic matter at low temperature, which by now is called the Bose-Einstein condensate. How do we get there? Well, let's start off by thinking about a cloud of monoatomic gas trapped in your favorite trapping potential. And if you were to look at the distribution of momenta, you would find a very nice regular Maxwell-Boltzmann Gaussian distribution of the momenta. And what Einstein and Bose tell us is that below a very low critical temperature, a significant fraction of those bosons condense into the ground state with a macroscopic wave function, which in this momentum profile would mean that your Gaussian would be sharper, and there would be this very large condensed peak at zero momentum sitting inside your distribution. Well, that is a prediction. How do we get there? And it required several technical breakthroughs to enable us to probe these low temperatures. And the first one was the development of laser cooling, where you shine laser light appropriately detuned to the transitions of your gas into your cloud, into your trapped cloud from all directions. And what happens is that now you absorb photons, but the gas radiates them into all directions, and that leads to a viscous force which reduces eventually the kinetic energy of the gas, so that step by step you are cooling this gas down. That gets you to around 100 nanokelvin, which is not yet quite there where you can observe these condensation phenomena, and it required another neat trick, which is evaporating the Maxwell tail by modifying your trapping potential, where essentially you lower your trap, you let some of the hotter of the molecules escape, you lose some of your gas, but what you are left with is colder. You do this multiple times, and eventually you end up with something that is colder than nanokelvin, and then indeed you do observe these types of condensation phenomena. Now I said, well, we reach these temperatures. How do we know? How do we know that we reach this temperature? And this is here where the first time we try to measure temperature. And the common way to do this is by a active imaging method called the time of flight method, which goes like the following. So you have your cloud of gas in the trapping potential, gravity is acting, you switch off the potential. What happens? Well, your cloud is starting to fall. And since you've started out with a velocity mixture in your cloud, some of them, the molecules are faster in some directions, some are slower, and that means that over time, as your ball falls, the size of the cloud is expanding and it's diluting. And what you can then now do is you can shoot laser light through it, and you will see how many atoms are able to absorb this laser light, and you can let it fall further, and you can shine again light through it, and your cloud will have diluted, and there will be less atoms available to absorb this laser light. And because the temperature determines the spread in velocities, and by that it determines how fast or how efficiently this cloud expands, the probability to absorb light also depends on the temperature. And so by recording these essentially the densities of your cloud over time, you can again read off the temperature of your original cloud. By that we have gotten one goal. We know the temperature of that cloud now, but we have a certain drawback, which means that we have just destroyed the system of interest during this measurement process. And the other interesting point is that for this here, only the Maxwell-Boltzmann distributed atoms are of relevance, because they contribute to the expansion, and they might actually be shadowed by this condensed peak that is sitting in the middle of your distribution. And that this is not just an academic debate. Let me show you here an actual measurement from 2015, where we see a time of flight measurement, and you can see at 54 nanokelvin, you still see, so you see this condensate peak, and then you see a faint sign of a Maxwell-Boltzmann tail around it. While at 16.2, you're already hard pressed to see a Maxwell-Boltzmann tail, and at 1.6, it's hard to see anything besides that peak. And so, how can we improve this? And this is where, for example, probes now come in. And here probes are a precision enhancer. The problem with probes here is we are facing the too cold to touch conundrum. There's nothing cold enough that we can stick into our gas. So the impurity or the probes must be impurities that are embedded in the ensemble and be in equilibrium with that ensemble. And one way that is currently used is you take a radio frequency pulse, and if you prepare your majority gas in a certain hyperfine state, say MF equals -1, you can now flip part of these states into a different hyperfine state, for example, MF equals 0. And these now flipped states will form coherent collective excitations called spin waves, and they will quickly thermalize with the surroundings. So now you have a majority gas of MF -1 and this minority spin waves that we also call magnons that have this other hyperfine state. The importance here is that you have just a very tiny amount of these flipped ones, so that it is not dense enough that they condense. So they are in thermal equilibrium, but they cannot yet condense. And you can already see where this game is going. Now you use a different type of RF pulse to sweep away all the majority gas, and you're left with the originally thermalized minority gas spin waves that you can now do a time of flight on. And if you do that, because they are not condensed, because they are too dilute, you now get this nice Maxwell-Boltzmann distribution from which you can read off the temperature quite nicely. And so here the probes have helped us to improve the precision of the measurement, but we are still destroying the system under consideration. So can probes help us to even overcome this? And yes, there is proposals on the market. Still, we are too cold to touch, so the impurities have to be embedded, or these probes have to be embedded in the gas. But now they don't necessarily have to be of the same species, so we can really think of them as impurities, which in this context would be called polarons, and that are embedded in this majority gas ensemble. And the challenge then is to find species that you can laser cool together, so that they are compatible for the laser cooling. And one proposal on the market is to take potassium as a majority gas and ytterbium as a minority gas. And you can, if you manage to all get them very cold, you now have these very hot ytterbium sloshing around in a in a soup of light potassium atoms. And that immediately rings the bell of Brownian motion if you have a heavy impurity in a bath of light particles. And maybe because we are so cold, this is already a quantum realization of Brownian motion. Now then we can ask, what are the properties of these impurities that would allow us to most precisely measure the temperature? And this goes into the field of metrology. So the science of measurement. And we can now ask, for example, what is the error in the measurement that you do if you are looking at a certain observable of your small system? And the error that you would make in the measurement is related to the intrinsic spread of the values of this quantum observable. That's the numerator. Then you have the usual square root of n in the denominator. That is how many measurements you've done. That should get you a smaller error. And then there's this sensitivity here, which is simply stating how dependent is your observable on the quantity that you're interested to measure. So if you have a property that doesn't depend on temperature, it will be very difficult to measure temperature with it. And that's simply what this chi encodes. For everyone who has done Monte Carlo or an actual experiment, surely for a classical random variable, we can beat down the error by increasing the number of independent measurements. I just wanted to mention that there is ways how to even overcome this classical limit to improve your error better than 1 over square root of n, which is related to what is called the Kammer-Rao bound. I will not go into details here, but simply stating that by exploiting the quantum nature of your observables, you can get better measurements than what you had with a classical random variable. So what is for me then interesting in this expression is this sensitivity function, because it simply says, okay, how does the expectation value of my observable change if I change the parameter, or the parameter of interest? So if I'm interested in measuring temperature, my observable should react to temperature. And I can, if I write this as such kind of a derivative, I can turn this into a optimization problem for finding the best observable. So I can ask via, say, a functional derivative, what is the most sensitive observable that gives me the highest sensitivity? And people have thought about this for quantum Brownian motion, and there they looked at what is the unique quantity that that would fulfill the optimum sensitivity, and you can define it through this so-called symmetric logarithmic derivative, which just gives you a condition for this for the extremum of the chi. And for quantum Brownian motion, you can actually solve all this explicitly. And what you find is that the optimal observable is a linear combination of the position spread and the momentum spread of your quantum Brownian particle. That would be the most sensitive quantity to measure. This is where, as a theorist, my work ends. I would now hand this to my friends who are doing the actual experiments, and they would then tell me, well, maybe this is not a quantity I can measure, or they can measure. So one would then have to discuss what is the closest thing to the optimal observable. But at least as a theorist, we should be able to present, so to say, these optimal sensitive observables. Okay, and I would like to use this opportunity to talk to you about one iconic model of an open quantum system, which is very related to this temperature measurement, which is really a heavy point-like impurity in a medium of harmonic oscillators. It is one of the founding models of this field, and in it we have our really a point particle, quantum mechanical point particle p squared over 2m. We have a bath of harmonic oscillators that is given by this.
Alexander, could I just
Yes.
interrupt for just 1 second about the previous slide?
Yes, please.
So are you envisioning a harmonic oscillator? Because x squared itself will grow in time, and so I'm confused. You were talking about Brownian motion, but x squared itself is changing in time, and so why is that an optimal thing? Or what time would you measure it?
So let's see. So
Or do you mean a harmonic oscillator?
yes, so it's harmonic oscillator, this quantum Brownian. So this is exactly the model coming from the model that I wanted to introduce in the next slide. I think it's similar to when you have classical Brownian motion. You can, by observing how the position spread grows over time, it's linear, and you have the diffusion constant in front. That's how you would then read off, say, the temperature of the environment. And I think the trick here is similar, that you say you observe the position spread of your particle, and you observe the momentum spread over time. And I would then now have to look into Mr. Meboudi's paper once more very carefully, how they exactly define then how they read off the temperature. But I think it's similar to this, what you would do in classical Brownian motion, with as the spread becomes linear over time, the prefactor tells you about the temperature.
Thanks.
Thanks. Okay, so we have our point particle, we have our bath of harmonic oscillators, and now, for the sake of this model, we couple the x coordinate of the harmonic of the point particle to the x coordinate of our of each mode, which is the creation annihilation operator added together, and you're allowed to parameterize the strength of the interaction per mode with this function g of k, which you provide as a modular of your system. And now what we're interested in is not the overall system, but just the probe. So we would like to formally trace out the medium degrees of freedom, and thanks to them being harmonic oscillators, this is possible in this case explicitly. We start out from the overall system and the von Neumann equation. We take the trace of the medium degrees of freedom on the left-hand side, and that means we have to take the trace of the medium on the right-hand side. And here I will just roughly mention the different steps that go in. The first approximation is the so-called Born approximation, that you assume that the initial density matrix is a direct product between the probe and the medium. This does not say anything about whether the probe itself is strongly coupled or the medium is strongly coupled. It just says how they can influence each other. So it might at first seem like a very strict restriction, but it actually is not as strict as one would assume at first. Then, why is this? How is this related to Brownian motion? Well, we have now a separation in time scales between the relaxation scale and the medium scale, and that means that the medium is updating much faster than information travels between the medium and the probe, and that means from the point of view of the probe, it does not need to take into account any type of memory effects, and that allows you to employ the Markovian approximation so that memory is discounted. Then the other one is the Brownian motion limit, where the probe time scale is much larger than the medium time scale, and that tells you something about how information and states are reshuffled inside your system versus in the medium. And that is exactly how you would expect it, the slow probe versus a fast medium. And taking all of this together, you can actually simplify this equation of motion, and you end up essentially with what is called the Caldera-Leggett master equation, which is a bit of an unwieldy beast here, but essentially it has three important ingredients. You have the time derivative of your probe density matrix. You have one part that looks like the von Neumann equation. It's the coherent dynamics part. And then you have essentially two more contributions. The first one is what one would call fluctuations. And if you had only this term, you would observe that you can pump energy into your small point particle. It would heat up, but it has no way to shed energy back into the medium, so it would become hotter and hotter forever. And this is where dissipation becomes important, which offers you a channel to release energy back to the medium. And it is the balance between those two that will eventually enable your small probe system to actually thermalize with the environment. We see a lot of commutators, anti-commutators somehow showing up here, prefactors. So at first sight, it looks somehow, it looks a bit ugly, but the important point is that there's a general mathematical structure hiding in this quantum Brownian motion equation of motion, namely that you can actually capture all of the physics by one operator, and that operator becomes a linear combination of the x and p operator of your small subsystem. So since we're only talking about the reduced density matrix, this should only contain operators related to the subsystem. And so you would, with this operator, you can write the evolution equation in this particular form. You have the coherent part, and then you have extra terms where your density matrix is now sandwiched in different ways between these operators called Linblood operators. And in front of this, you have what is called then a damping rate for each possible of these Linblood operators. So in quantum Brownian motion, there's just one of these operators, but you can have multiple operators, and each of them get one of these damping rates. And it is these Linblood operators that somehow encode many of the relevant residual interactions between the probe and the environment. and it is this type of or this form of the evolution equation is deriving this was important because it could be shown that any Markovian open quantum system can essentially be written in terms of such kind of so-called Linblood equation. And why is this important? Because you can also prove that if you can write it in this form, the time evolution will conserve the relevant properties of the density matrix, its positivity, its hermeticity, and the unit trace. Derek, did you have a question? Sorry, you switched on your
question, just paying attention.
Okay, cool.
Alexander,
yes.
I do have a question though.
Yes, please.
Good that you stopped. I see that essentially the only information that you have about the system is the temperature. Everything else is gone. Is that correct?
There is this innocent gamma k here, and the gamma k is showing up here in the Caldera-Leggett. We only have one Linblood operator, so there's just one gamma, and this gamma is a function of these couplings between the point particle and the bath. So the complicatedness of the interaction, the complexity of the interaction is at the moment hiding in this gamma, but it is an explicit, you can explicitly write down the gamma as a function of G and T.
The reason I'm perhaps asking, maybe that will explain. You could imagine different type of systems. For example, I don't know, fermionic gas, bosonic gas, or let's say fermionic gas in a strong magnetic field with some quantizing effects. And in all of those cases, you could define the temperature perfectly the same way, but the spectrum of the actual medium is very different. So how is that felt here?
So the spectrum of the medium would exactly change the gamma, and it might actually, and this is something that I didn't go into detail, it can also change the H probe. So in the H probe, you can, this is not necessarily just the p squared over 2m that you originally had, but this can have additional contributions that arise exactly from the interactions and the specific structure of and the spectrum of the interactions.
I see, thanks.
Sure. And because this gamma is exactly, so thank you for bringing the gamma up, because I called it a damping rate, and one should say, how does this connect to a damping rate? And one of the sanity checks one can do is to try and compute the Erdfest equations of motion from this kind of quantum Brownian motion Caldera-Leggett model, and you would see that the velocity equation is unmodified, but the change in momentum now gets a correction that is proportional to the gamma, and that again now translates into a time scale or an inverse time scale on which your expectation value of the momentum goes to 0, which is nothing but randomizing your originally directed momentum. And that means you only get that far on average inside the medium, again, determined by the initial directed momentum you imbue your particle with, and this gamma. And this is why we call it a damping rate. And it is really, that depends very much on the specific details of the medium that you're using. And one other sanity check is to look exactly at this the position spread, and at least for late times, it's very satisfying to see that it becomes linear, which makes connection with the standard Brownian motion, the classical Brownian motion. And again, you get a prefactor that goes with the linear with the temperature, inverse proportional to the mass, and inverse proportional to this damping rate. And with that, all ingredients are ready. You can solve now this quantum Brownian motion system, and you are ready to make predictions for precision low temperature thermometry using quantum Brownian impurities based on, for example, this position and momentum spread statement. Of course, this is just the simplest scenario as possible. We have neglected possible memory effects. That's a hot topic in the condensed matter community, to go beyond the Markovian approximation. And surely you can imagine that this arbitrarily makes things more complicated. But the original idea is what I wanted to present to you here. Okay. Now, we've looked at the coldest matter in the universe. Let's head over to the hottest matter in the universe, the quark-gluon plasma. And this story begins in 1965, where Hadron studies the statistical properties of hadrons and deduces that there should be a new phase of nuclear matter at high temperature, which we now call the quark-gluon plasma.
No, he didn't do that. He was arguing against quark-gluon plasma. He proposed that all temperature is limited by Hadron temperature.
I see. So I should be careful in with this.
He was arguing exactly the opposite, that you cannot get beyond Hadron temperature.
Well, there were no real quarks in 1965.
Yeah, that's another reason why he did it. But if you read the paper, this is what it said.
I'm happy to. I'm very thankful for this comment, because that might be the incorrect but enthusiastic interpretation of a later born scientist.
Yes. And he wrote later a paper which was entitled, his paper, How We Came to Phase Transition by Trial and Error. That was the title of his paper.
Thank you for the comment.
But he said that something unusual should happen around that temperature.
In the
conclusion,
this is relevant to the talk. In the conclusion, he said that, in the conclusion of 65, he said that this is the temperature of hell, and anybody who disbelieves in his calculation can go and measure themselves. It's a wonderful conclusion. So
yes,
you're
wonderful, but wrong. But wrong.
Yeah.
We get to higher temperature than that, and we're still here, right?
Yes. Yes.
Anyway, let's proceed with the actual talk, though.
Yes, because obviously nuclear matter around us is made up of strongly interacting quarks and gluons confined into hadrons. I'm preaching to the choir, as I see from the participant list. We know from lattice numerical simulations that there is a crossover phase transition at around 2 × 10⁻¹² Kelvin, above which quarks and gluons get released from their confinement and form eventually what historically was called the quark-gluon plasma, which invokes the picture of a gas-like medium that is weakly correlated due to asymptotic freedom. And surely it was a surprise in the beginning to see that this state of matter just above the crossover phase transition behaved much more like a liquid, which implies strong correlations, very different from a plasma indeed. Why is it of interest to think about the quark-gluon plasma? Well, it has filled the universe shortly after the Big Bang. That is enough for me to already be excited. It also possibly exists inside of neutron stars, even more excitement. So this is really something tangible. We are doing gravitational wave measurements to exactly establish whether in such kind of collisions, for example, the quark-gluon plasma is created. The theory basis here is a quantum field theory called quantum chromodynamics, a field theory of quarks and gluons endowed with a tripled value charge called color due to historic reasons. And where are heavy ion collisions carried out? Well, again, many of you know we have large international collider facilities such as the Large Hadron Collider. Here a sketch with the different pre-accelerators until the 27-kilometer ring housing 4 major experiments, where here one I've shown Alice with 2 puny humans to scale for her enjoyment. And what happens now as you bring these accelerated particles into collision is that, and this is the simplest type of collision, you can collide, for example, two protons in this machine. And what happens is that the vast amount of kinetic energy that is residing in the projectile is transformed into new quarks and gluons. And what you will find is a essentially isotropic spray of these new particles coming out of the collision center. Now, in a relativistic heavy ion collision, we have now many more particles participating in this collision, so that in the overlap of the two projectiles, you can now create a vast number of quarks and gluons that now may meet each other in this collision center, exchange energy and momentum efficiently, and we believe form a locally thermal quark-gluon plasma. And because the initial state of this collision is highly anisotropic, this anisotropy now imprints itself in the spray of particles that emanates from the collision center. And so by comparing the PP result, the proton-proton collision, with the heavy ion collision result, we try to infer first the presence, and is the second step, the properties of the medium created in the collision center. And one of the properties we might be very much interested in is a temperature. We said there's a local thermal quark-gluon plasma. What is the temperature? And well, coming back to the blacksmith of old times, the first thing we can do is passive imaging via radiation thermometry. We look at the electromagnetic radiation emanating from the collision. So we have our proton-proton collision. A few photons might shoot out. They come, we think of them as emanating perpendicular to the beam direction. This is why we call this momentum transverse momentum that we measure of these photons. And in a heavy ion collision, you would now have a medium that might generate many more photons, again, that you would then measure in your detector. And let me show you this slightly busy plot here, which is the spectrum measured of photons versus this transverse momentum. And there are three data sets here, red, green, and turquoise, and they amount to collisions at different so-called centrality, how much there is overlap between the projectiles. The more central the collision, the more energy there is in the collision center, the hotter it is, you would intuitively assume. And there's some interesting things that we can see from these collisions, from these measurements. The first one is at high transverse momentum. One would assume that the photons come actually from collisions of the quarks in the individual projectiles. And that would mean that essentially the difference between a proton-proton and a heavy ion collision is simply scaling up the proton-proton result to the amount of individual collisions of projectile quarks that happened. And this is exactly the black curve that you see overlaid here. It's the PP result for the same measurement, just scaled up according to how many nucleons have participated in this collision. And you see that for large transverse momentum, this seems to be reproducing the result quite well. On the other hand, at low transverse momentum, this is where you would expect that maybe a medium that is created in this collision can radiate off photons, and they would add on top of this PP result, because there's something qualitatively different now than what would happen if you just scale up a proton-proton collision. And that was very exciting because people now see this excess over the rescaled PP at low transverse momentum, and very brave men and women now fitted a Maxwell-Boltzmann distribution to this lower part of the spectrum, and lo and behold, obtained temperatures between 300 and 400 MeV, which is larger than the temperature that is needed to generate a quark-gluon plasma. That excitement, however, was damped a bit because afterwards theorists came up with different explanations for this Maxwell-Boltzmann tail that you can get even without a quark-gluon plasma present. So the source of those low PT photons, I would say, was not clear enough so that you could directly establish that this temperature should be connected to the temperature of a quark-gluon plasma. And that brings us to the probe-based measurement of temperature in a heavy ion collision that is very dear to my heart, which is through heavy quarkonium. So here we have the issue of too fast to watch. We cannot interrogate the collision center with a laser. We need to use collision remnants to do the job. And one of the probes to now have in mind is a pair of a heavy quark and anti-quark. Heavy might be a bottom quark or a charm quark. And similarly to having spin singlets and spin triplets, now you can have different combinations of these quark anti-quark pairs that because of their color configuration, and so they can come up in either a color, so-called colored singlet configuration that is attractive, or a color octet configuration that is repulsive. And if they come out as a color singlet, they may stick together and form a bound state that is then called quarkonium. Either charmonium is a charm quark pair or bottomonium for a B bottom quark pair. And these are very interesting particles because in vacuum, their decay into hadrons is suppressed by the OZI rule and the quantum numbers of this object, and that gives them very small decay widths, kilo electron volt widths for a strongly interacting system that is translates into extremely large lifetimes. And it also means that there's a significant decay channel into dileptons, which provides our experimentalist friends very clean experimental signals, be it in dimuons or dielectrons, to measure these particles. For a theorist, heavy quarkonium is interesting because of the heavy mass of the quarkonium of the heavy quarks relative to all the other scales of the strong interactions. For example, the intrinsic scales of quantum fluctuations lambda QCD. One can actually go over and use a non-relativistic language to describe these bound states in terms of a simple two-body potential that I've just sketched here, modeled via the so-called Cornell potential. You have a Coulombic part at small distances that's related to one gluon exchange or asymptotic freedom. You have a linearly rising part related to confinement, and eventually this string breaking will flatten off this potential, and that can sustain certain bound states. And you can compute this potential directly from QCD. And if you now look at what happens in such kind of a proton-proton collisions, there will be a number of these quarkonium pairs flying out, and the CMS collaboration has measured these, and you can nicely see that 3 species of bound states emanate from this collision center, which correspond to the ground first and second excited state of the bottomonium system in this case, measured as dilepton pairs. Now, what changes in a heavy ion collision? Well, we will have the initial collision. We will have the creation of, say, a bottom anti-bottom pair. They might quickly snap into a bound state, and then they find themselves in all this debris that they are floating around. And now the question is, what happens if we have such kind of a bound state inside this medium? Does it survive? How long does it have to survive? Will we be able to measure it flying out of the collision center or not? And what makes this interesting for a theorist is that it's still a non-relativistic particle because the heavy mass of the quark is still larger than the temperature. And you have a heavy thing wobbling around in a bath of light objects. Again, this cries out for Brownian motion concepts to be applied, and the presence of the quark-gluon plasma surely will now modify the interaction potential between these heavy quarks. And so for a long time it was known that this potential that sustains the bound state or not will be modified with an analogy with electromagnetic plasmas, where if the phenomenon of the biscreening sets in. Similarly, one expects that this potential is actually the biscreened, and work is ongoing to extract the values of this potential from the lattice. And it tells you, however, that now you cannot sustain the same number of bound states, so something will happen to your system. And if you do the same measurement as you did before, now in a heavy ion collision, indeed, we see that we find remnants. So the red curve is appropriately rescaled PP result. The blue curve is now the heavy ion result. And we see that the ground state still has a significant contribution, but the more weakly bound first and second excited state are almost gone. And so this really gives you now the idea, if we could understand how the different quarkonium states react to the presence of the medium, this gives us, we could reverse engineer what are the temperature conditions inside such kind of a collision. And why can we not just use caldera-Ledgett? We derived a point particle in a hot medium. Well, our probe now has finite extent and carries this extra color charge, and so that means you need to derive a new Linblood equation. And I've seen that some colleagues are around who also have derived Linblood equations for heavy quarkonium. Here I will specify on one particular one. That's the only. I only have time to guide you through this one, so I asked my colleagues to kindly accept my selective view here. But essentially, what had been done is that a long-time collaborator of mine, Yukinawa Akamatsu, had in 2015 derived a quantum Brownian motion Linblood equation from QCD at high temperature, and saying high temperature means it uses a weak coupling approximation. And in that case, you have several Linblood operators, but you can write it as a Linblood equation. So all of our intuition is still there. You have a coherent part with a interaction potential that might now be changed by the medium interaction, and you have the interactions with the medium encoded in these Linblood operators. And indeed, the in medium Hamiltonian has a p squared over now mq, because we have two particles, and a real potential that is the bi-screen. So the bi-screening comes from the medium particle interaction. But now what happens for these Linblood operators? And I just, even though I put the formulas here, let's think first about what's happening behind the scenes. In QCD, quarkonium interacts with the medium via gluon exchange, and that entails two things: a momentum transfer and a color rotation. And if we keep that in mind, these unwieldy expressions for the Linblood operator actually make sense, because we have two of them, two contributions, one for the quark, one for the anti-quark. They contain a momentum transfer, K, and they contain color rotations through the color matrices, TA. There's a minus sign in the second term that distinguishes quark from anti-quark. And if you since in the caldera-Ledgett, we were able to identify the physics of fluctuations and dissipation in this whole Linblood operators. And here you can do the same. The one here corresponds to fluctuations. If you have only that, you can heat up the system, but it will never shed energy. And if you have the second term, then you can shed energy back to the medium, which will allow you to thermalize. The strength of these interactions is governed by this function d. And if you look at this function d in position space, you will find that it has a peak around the origin. And that means there's a scale hiding. This peak represents a scale. And this is a new scale. This is the correlation, the color correlation length of our medium. And that tells us we now have two effects. We have the bi-screening that is relevant, and we have the coherence of color rotations acting on our quark and anti-quark. And I see that I'm out of time, but I hope that you can give me 2 more slides because I would really like to give you this message, that for many years we have been thinking about quarkonium in terms of screening only, and this is what we know. So you have your screening radius. If it is larger than your QQ-bar pair, the bound state can be sustained. The radius becomes smaller and smaller. It becomes more difficult for the gluon to reach between the Q and Q bar. And if the screening radius is too small, the gluon cannot reach between the Q and Q bar, and the binding is gone. But now you have a different effect. You have the decoherence. of color rotations, where if the correlation length is larger than your QQ bar, well, you will have coherent rotations on your quark and antiquark, turning a color singlet into a color singlet. But now if the color correlation length becomes smaller and smaller, eventually it will lead you to do uncorrelated rotations on your quark and antiquark, turning a singlet, say, in an octet, and that is not attractively bound. And by that, you're destabilizing your QQ bar state, even if the gluon was able to reach between the Q and Q bar. And these are nice pictures, but we should try, and I would like to show you somehow where we now are with turning this into numbers. So we have now a first one-dimensional proof of principles computation of this Linblood equation, where we and I show you here an example where we start. The red one is the ground state, the blue one is the excited state occupation number. And in the first one, we start with 100% ground state and 0% excited state, and we evolve it. And then we run a different one where we start with 100% excited state and 0 ground state, and also let it run. And we find that they all go to the same steady state at late times. Steady state is already encouraging for thermalization, but it's not enough. So now we have to actually look at the distribution of the states in the steady state. And this is down here, the occupation numbers versus the energy of the state. And this is a log plot. So a linear relation here is an exponential, and the inverse slope is what you would call an effective temperature of your system. And the number you fit agrees very closely with the temperature we've endowed our environment with. And that was very encouraging because it allowed us for the first time to actually thermalize, even in 1D, this QQ bar system in a fully thermal fashion at late times. And that was one important step towards promoting now the study of heavy quarkonium, I think, in heavy ion collisions to a precision thermometry tool, because the community, this was one example for an evolution equation, but there are different evolution equations out on the market capturing different regions of temperatures and different quarkonium species that now get a closer look from first principles on the evolution of these quarkonium particles, eventually hopefully allowing us to understand the reshuffling of states well enough that we can take the CMS measurements and reverse engineer from the suppression we see there relevant hints on the temperature that has existed in the collision center. And with that, I would like to summarize. I've hoped to show you that open quantum systems, thought of as impurities that represent quantum probes, play an essential role in precision thermometry at vastly different energy scales. We looked at Bose-Einstein condensates and the Quark-Gluon plasma, while at the same time the theory framework developed to describe these open quantum systems, such as Linblood equations, master equations, seem to provide a common language among formerly disparate research fields. And to me, this means that there is still exciting prospects for collaborations between the ultra-cold atoms and the heavy ion collision community on impurity physics that goes well beyond quarkonium. You can think of jets as impurities. You can even think of the phenomenon of hadronization in some sense as a tracing out of parts of your phase space. And so I do believe that open quantum systems are an exciting field in the future to connect low energy physics and heavy ion collisions. And with that, I thank you for your attention.
Thank you very much for a nice presentation. Now let's go to questions. And the first question is from Edward Chirac.
Just general theoretical question. People have used this problem with quarkonium by other standard ways, with Langevin equation, Fokker-Planck equation. What is the difference between Linblood and these other tools? So they all describe relaxation, right?
Yes, thank you for this question, because one of the important steps that the community now made was exactly to answer this question, because there were a lot of phenomenological models. You had the rate equations, you had the Boltzmann equation community, you have the Schrödinger equation community out there, all doing these simulations, and we now can derive, so to say, these phenomenological models by first deriving a Linblood equation in a certain scale hierarchy of time scales, and then making additional assumptions that lead us to the corresponding phenomenological model. So Xiaoyun Yao, who is in the audience, he, for example, together with Tom Mayen, derived a Linblood equation using potential NRQCD that you could then, under certain assumptions of time scales, you could then reduce to a Boltzmann equation and further on to a rate equation. So you can now follow the chain of approximations that go into deriving the Boltzmann equation from QCD, recoupling, timescale separation, and such. Similarly, for the Schrödinger equation, we showed, so once you have this quantum Brownian motion Linblood equation, you can show that it is equivalent to a stochastic nonlinear Schrödinger equation. So that explains some models that use nonlinear Schrödinger equations for quarkonium. But then you can say, okay, if you go to the dissipationless limit, then this reduces to a linear stochastic Schrödinger equation. And if you then go to the adiabatic limit, it reduces to a deterministic Schrödinger equation. And then you arrive at that type of phenomenological model. But again, you now know what is the chain of approximations that goes into that, and that limits the range, or it should be possible to determine the range of validity of these different phenomenological models. And I think that is one of the important contributions that the community has come up with over the past years.
Okay. The next question then is Giorgio Torrieri.
Hi. First of all, thank you very, very much for this talk. I mean, this is one of the talks I'm glad will be on YouTube, because I'll make there is people who, for people who are learning this stuff, this was
awesome.
Really
thank
good.
You.
Yeah, just to say. Now for the question. I mean, in other contexts, the Caldera-Leggett model has very non-trivial effects with scale separation. I mean, for example, I know that with potential well-type situations, you have infrared effects which contribute a lot to decoherence. And then you have coherent oscillations, which are ultraviolet, and you have critical points and stuff like the scales mix. And we also know that in QCD, the infrared part of QCD at arbitrarily high temperature is also very tricky. Non-perturbative stuff goes away. So what happens with your Linblood equation?
Yes, very, very good point, valid point. In some sense, I yield a bit, but so this is something that the community definitely is interested in. We need to go beyond the weak coupling approximation and need to somehow be able to incorporate non-perturbative information. And one way how this is done at the moment is by using, as let's say, focusing on a subset of quarkonium particles. So there is the Munich group has, for example, said, okay, let's take very small quarkonium particles, and if you then you have the size of the quarkonium as an additional expansion parameter, and you can then derive a Linblood equation that does not make reference to a weakly coupled medium, and instead arrive at a Linblood equation that is governed by non-perturbative transport coefficients. And these transport coefficients can now contain non-perturbative physics from the magnetic scale, the electric scale, to the UV. And so this is then, for example, what now the lattice community is trying to do is to determine those kind of transport coefficients from first principles that should then include all this extra information that would be unavailable in a perturbative, in a weakly coupled medium. This is essentially all I can say so far. We have since we analytically have no control over the strongly coupled medium, the strategy I see will be that we have to reformulate our the Linblood equations and its parameters in terms of, again, some sort of spectral quantities that we can then evaluate in lattice QCD, and that will then contain these infrared effects. While I'm not sure whether we will be able to analytically separate them. At the moment, all of our approaches are at first trying to get a handle on the non-perturbative physics in some effective manner. So we were not close to having a same Caldera-Leggett type, so to say. We cannot take apart the system in the same way.
Okay, you are muted, Giorgio. You were saying something. I saw the.
Oh yeah.
But I think he was saying thank you or something like that, judging from my reading. Anyway, the next question is Victor Raev.
Thanks for an interesting talk, and I have a couple of questions concerning the formal properties of Linblood equation. And well, first question concerns the preservation of positivity of density metrics, which you mentioned. Is it already has a property of time irreversibility, so that positivity is preserved for positive time, or it's still preserved also when time is decreasing? And second question is, it seems that to derive the equation, I need to interchange the operation of taking the trace and time derivative. Is it always possible to interchange the order of these operations?
Okay. I think part of it comes from the assumptions we make. For example, this Born approximation, that I think helps us to keep apart the physics of the probe and the medium in a controllable fashion. If we can argue for this approximation, then I think we are safe with making these kind of switches. But honestly, I have not spent enough time on the formal aspects of the Linblood equation to give you an expert statement on this. The evolution that that it describes is non-unitary, so you would not be able to go back to the same outset if you reverse the time arrow. For that, anything that goes beyond, so adding the Linblood term here destroys that property.
Actually, QCD evolution equations also typically preserve positivity only in one direction. So maybe so maybe it's also a sort of irreversibility is also can be seen here, which seems to be interesting. Thanks.
Thank you.
Okay, thank you. Any other questions from the audience? I kind of have a very simple, maybe even naive question. When you were talking, I still couldn't help noticing that you are primarily concentrating on the temperature. Temperature is one of the characteristics of this kind of systems, but not the only one, and perhaps not sufficient to describe the system fully. Equation of state, as one of the examples, is very important in many cases. So are you saying, concerning that discussion we had during the talk, that essentially all of that information is hidden in the gamma parameter? And if so, then what's the correct way then to choose the gamma if you do not know the system truly from first principles?
Well, so the gamma should come out of, the gamma comes out of your model in the Caldera-Leggett. It really, you specify as a model the interactions of your point particle per mode, and that gives you the function gamma of k. In the derivations of the Linblood equations for quarkonium, the success lies in actually providing a QCD-based statement for that gamma. And that is what we would call, we have established a Linblood equation from QCD, that we make exactly this connection. So either it is through a weak coupling computation that we would determine it, or in the case of these small quarkonium states as a transport coefficient. But this is what needs to come out of your computation if you establish a Linblood equation. What I think is very interesting about this, and how the condensed matter community has actually used this, and I'm wondering how much we can in the heavy ion or in the high energy community benefit from it, is to really think about this as a question of metrology. Is there a systematic way how to define the best observable for a certain property? Because exactly as you say, maybe I'm interested in shear viscosity or bulk viscosity or other properties of my system. Then there should be, at least in principle, the most sensitive observable related to that medium property. And it should come out of this type of finding the optimal observable for a certain, to be dependent on that medium property. Whether that is then a useful and practical quantity is a completely different question, but at least we should be able to establish what would I have to measure of a quarkonium particle to read off most sensitively the viscosity of the system. Which of course means you need to somehow have it included in how the medium interacts with your quarkonium, because at the moment we are only deriving all of these equations from a static background. Everything is nice so the medium is in equilibrium. The probe particle doesn't have to be in equilibrium, but the medium usually is taken to be in equilibrium to make things handleable. But this you could relax and then try to connect what kind of property of your quarkonium or your jet is most susceptible to viscosities and such.
Right. But what I had in mind may be even simpler. So you gave an even better answer than I was expecting for. But the simpler thing that I had in mind, something like, well, the plasma could have non-zero baryon chemical potential, or the plasma could have magnetic field present. Those are also kind of equilibrium, kind of very basic properties, but they do modify the system quite a bit.
Yes, and they would, I guess, if you now had, instead of a point particle boson, you would have a fermion here. There would be some sigma B thingy showing up, so that somehow there is a relation between the external magnetic field present generated by the medium, and that should eventually show up in the master equation. And by that you can take the derivative of the reduced density matrix with respect to that parameter and ask again, okay, how sensitive are my standard observables to it, and what it would be the best observable to measure it.
I see. Yeah, it makes sense. Thanks. Anyway, I don't see any raised hands. So before I wrap this up, we do have actually one. Anyway, let me use this opportunity first to thank you again for giving a very nice presentation, but we still have another question from Travis Duo. Please go ahead.
Hi, sorry for being like the last question. I missed most of the talk, actually. I came in for like maybe the last 15 minutes or so, but I'll definitely be going on YouTube to watch the first 45 or so minutes. But I had just had maybe a naive question. You said that you can make this assumption that the the heavy quarks are non-relativistic because their mass threshold is much smaller than the temperature, and that makes sense if you think about the heavy quark just kind of being born there, right? But why can't I have, like, the heavy quark being born with some in the lab frame or in the center of mass frame just being born with some initial large 4 velocity or something? Like, why can't it just have been born intrinsically relativistic in the sense of, like, it's
well,
right?
you have the center of mass momentum that can be still a large momentum as it's flying out, but what is relevant for us is that the momentum exchange between the QQ bar is small. So if it's in a boosted frame, surely that can be a quarkonium almost jet-like thing. But I mean, the thing, if you sit yourself in the rest frame of the quarkonium, that's where it's still non-relativistic. And that's
otherwise it's unbound.
And it's unbound. Yes, exactly. It wouldn't be able to sustain in a bound state. Yes.
Interesting. Okay. Thanks a lot.
And sorry, now I have, you gave me some something to say. So sorry, I have to say. So of course, one of the things that are very interesting and that are, I think, not very well understood is exactly the earliest moments of this collision, where you have the QQ bar pair produced, and now we say, oh, according to the inverse binding energy, there's some sort of a 0.1 Fermi time scale where this now might stick together, but we don't. This is really just guessing. And what we are trying to now do is to do first simulations, very crude, with so-called classical statistical simulations in the Glasma phase, to see, can we actually simulate a quantum QQ bar pair, non-relativistic, in such kind of a highly gluon occupied environment? Can we see it stick together? And that would maybe give us a first systematic handle on eventually getting beyond these rule of thumb estimates for the creation of the QQ bar state in the earliest moments.
Yeah, that makes a lot of sense. Okay, thanks.
Cool.
Okay, thank you. Once again, thank you very much for a nice presentation. And with this, we will wrap up the official part.